Faithfully sharing insights, we explore the world's best books. Hi, this is Sally from Sally's Book Talk. Today, we're diving into the book Exercise Transforms the Brain. Do you enjoy exercising regularly? What's your favorite type of workout? Feel free to share your thoughts in the comments. We all know exercise strengthens the body, but that's just the basics. You know, the key benefit of exercise is brain health. Exercise boosts brain chemicals to sharpen learning and focus, lift your mood, ease stress, balance hormones, and even reverse age-related decline. These perks come from the author John Ratey, who's studied the brain exercise link since 1984. John Ratey is a renowned psychiatry professor at Harvard Medical School focused on exercise brain research. In 2012, the APA officially made exercise a treatment for mood disorders like anxiety and depression. The author played a key role in this achievement. Today's book is the result of 20 years of dedicated research packed with real-life cases and science. It has 9 chapters. The first 8 cover exercise's effects on cognition, emotions, hormones, aging, and more. Chapter 9 offers practical exercise recommendations. Published in 2008, it's had 16 reprints and 10 translations, becoming a global bestseller. In education, it sparked the Active Kids program. It suggests kids aged 4 to 10 do 40-minute morning workouts 2 or 3 times a week. Now, schools in the US, Canada, Japan, South Korea, and others are involved. Next, I'll break down the book into 4 parts for you. First, how exercise boosts brain power. Second, exercise's impact on mood. Third, how it tweaks hormones and fights aging. Fourth, the best ways to exercise smart. Let's dive into the first question: how exercise sharpens your mind. Cognitive skills, like learning, focus, and memory, depend on brain signaling. Brain signals travel through nerve cells, or neurons. Neurons have 3 parts. The soma stores genetic material, and dendrites receive information. The axon sends out information. What it transmits is called electric current or electrical signals. But axons and dendrites between neurons aren't connected. There's a gap called a synapse. Neurotransmitters help electrical signals cross this gap. Scientific research shows about 80% of brain signals are transmitted through the same neurotransmitters: glutamate, which stimulates nerve impulses, and GABA, which inhibits them. When transmitting electrical signals, these 2 neurotransmitters must stay balanced. After an electrical signal reaches the dendrites, neurotransmitters bind to receptors there. Think of it like a key fitting a lock. Channels on the neuron open, the signal passes through, and neural activity happens. A neuron can get signals from many others and send info to multiple neurons, forming a network called a neural circuit. For learning and boosting memory, info needs constant flow through neural circuits, plus help from the prefrontal cortex, the brain's command center, and the hippocampus, the memory hub. For example, say you're learning the poem Thinking of My Brothers on double ninth day and seeing its lines for the first time. When you read I Miss My Family All the More on festive days, the info goes from your eyes to the prefrontal cortex, which acts like the brain's boss. It gets the info and starts directing the neural network. And so, for instance, the prefrontal cortex tells the hippocampus to work. The hippocampus deals with memory. It quickly recalls, I miss my family all the more on festive days. It compares this sentence with scattered memories of missing family in different brain areas. The hippocampus calls them all out. After comparing, the hippocampus acts like a cartographer, drawing a new map that includes your family longing and the new sentence, then sends this map to the prefrontal cortex. Once the prefrontal cortex gets the map, it means the neural circuit for this sentence is built. That's how you learn this sentence, and the whole poem works the same way. After learning, the brain stores this poem's info in the basal ganglia, freeing up the prefrontal cortex to learn new things. When you often need this poem, like in exams asking you to write the first 2 lines, alone, a stranger in a foreign land. I miss my family all the more on festive days. With constant repetition and practice, more synaptic connections form, helping you firmly remember these lines. Far away, I know my brothers climb the heights, wearing dogwood, missing one. Because it's not tested much in exams and used less in daily life, then the synaptic attraction for these lines weakens and the info fades. That's why many people don't remember the later lines well. The author gives a vivid analogy. Neural synapses are like modeling clay. They're plastic, and plasticity is key to memory and learning. The discovery of synaptic plasticity came from Columbia University neuroscientist Eric Kandel, who won the Nobel Prize in 2000. So why does exercise help with learning? First, exercise boosts levels of BDNF in the brain. BDNF is a protein molecule, full name brain-derived neurotrophic factor. If you imagine the brain is a highway, glutamate and GABA are like cars, helping transmit messages.
When BDNF increases, it boosts synaptic signal strength, acting like a traffic controller, speeding up the cars.
BDNF is also like a highway designer, maintaining it to be smoother and clearer. Scientists have done experiments where adding BDNF to a petri dish makes neurons grow stronger. So they also live longer. So more BDNF promotes neuron growth and strengthens the brain's neural network. Secondly, exercise directly acts on the hippocampus, prompting it to produce more neural stem cells, which multiply and become neurons when stimulated. More neurons in the hippocampus mean more synaptic connections, aiding memory.
In a 2007 human study, German researchers found people learned vocabulary 20% faster after exercise than before.
Exactly. Beyond learning and memory, exercise also boosts attention. Our brain has an attention circuit primarily governed by norepinephrine and dopamine. These two neurotransmitters work together to regulate it. When we focus, norepinephrine and dopamine reach the amygdala, the brain's emotion hub, calming it down. Meanwhile, dopamine activates the reward center to optimal levels, sending pleasure signals to the prefrontal cortex. This alerts the prefrontal cortex to prioritize tasks, ultimately sharpening focus. Many restless, unfocused children may have dysfunctional attention systems, clinically called ADHD. A 2016 U.S. survey showed 9.4% of children have ADHD. That's 1 in 10 kids struggling with focus, memory, and hyperactivity, and adults too. The survey found about 4.4% of adults also have ADHD. The ADHD brain lacks sufficient norepinephrine and dopamine, failing to calm the amygdala, leading to outbursts or impulsive behavior. This explains common ADHD symptoms, which also affect the reward center. With low dopamine, the reward center stays understimulated and won't signal the prefrontal cortex to engage. That's why ADHD makes focus difficult or only possible under high stimulation. Exercise helps ADHD first by raising the amygdala's emotional threshold. A threshold is a boundary line. Higher boundaries make the amygdala less prone to rage. Second, exercise instantly boosts norepinephrine and dopamine, calming a reactive amygdala. In fact, ADHD medications work similarly by elevating these neurotransmitters. All right, let's recap the first part. Cognitive abilities rely on brain signaling, and through neural circuits formed by synaptic connections, exercise boosts levels of brain-derived neurotrophic factor, BDNF, promoting neuron growth and strengthening the brain's basic neural structure. Exercise also directly prompts the hippocampus to produce more neural stem cells, aiding our memory. When attention wanes, like in ADHD, exercise raises the amygdala's emotional threshold, boosting norepinephrine and dopamine secretion, leading to emotional stability and increased learning motivation. And one thing, now that we've covered cognition, let's turn to the second question. How does exercise affect mood? In modern society, people often face stress from family, work, relationships, and other areas. Some may feel mildly alert, while others feel completely overwhelmed, sinking into despair. So how does stress impact the brain, even developing into emotional disorders like anxiety or depression? When people feel stressed and tense, the amygdala, our brain's emotion detector, immediately sends signals. stimulating the adrenal glands, releasing different hormones at various stages. In the initial stage, the adrenal glands release norepinephrine. Once in the bloodstream, it increases heart rate, blood pressure, and breathing. That's why you feel tense, heart racing, and restless when stressed. Meanwhile, the hypothalamus also receives signals, prompting the pituitary gland to work. The pituitary gland is the body's most crucial endocrine gland. The only pea-sized, it's the master switch for regulating hormone levels. The pituitary gland directs the adrenal glands to release cortisol, a hormone vital for human survival.
When your body senses a threat in the environment, it instantly reacts, preparing for rapid action. Fight or flight. Let's see exactly how cortisol works.
In this process, cortisol's first job is like a traffic cop, signaling the liver to speed up, converting fat and protein into glucose for quick energy. But this glucose only flows to stress-related areas like the amygdala and hippocampus. Cortisol blocks pathways to other organs, starving thinking-related regions of energy, explaining why we can't think clearly under high stress. Due to massive energy consumption, cortisol directs you to replenish food to restore blood sugar to normal levels. So you intensely crave high-sugar, high-calorie foods like donuts, bubble tea, ice cream. Their sugar fat content far exceeds bodily needs, and the excess gets stored as belly fat. Since the abdomen is near the body's center of gravity, storing energy there doesn't affect movement balance, hence faster fat accumulation than limbs. It's also where organs are located, so fat prioritizes abdominal storage for protection. That's why high stress often leads to weight gain. The amygdala also signals the hippocampus to map and record memories. As the saying goes, once bitten by a snake, you fear rope for 10 years, because the hippocampus encodes anxious emotions into lasting memories.
Meanwhile, cortisol activates proteins in the hippocampus to create more nerve cells, reinforcing this memory. Cortisol dominates. These new cells could form other memories, but cortisol blocks them and disrupts access to existing memories.
Secondly, exercise directly acts on the hippocampus, prompting more neural stem cells that multiply into neurons when stimulated.
More hippocampal neurons mean more synaptic connections, enhancing memory. In a 2007 human study, German researchers found vocabulary learning speed increased by 20% post-exercise. Exactly, exercise also sharpens attention beyond just learning and memory.
Our brain has an attention circuit primarily governed by norepinephrine and dopamine.
These two neurotransmitters jointly regulate it.
When focusing, they reach the amygdala, the emotion hub, calming it down.
Simultaneously, dopamine activates the reward center to optimal levels, sending pleasure signals to the prefrontal cortex.
This alerts the prefrontal cortex to focus on the matter, ultimately sharpening attention. Many restless, unfocused children may have dysfunctional attention systems, clinically called attention deficit hyperactivity disorder, ADHD. A 2016 U.S. survey showed 9.4% of children have ADHD. That's 1 in 10 kids struggling with focus, memory, and hyperactivity, and adults too. The survey found about 4.4% of adults also have ADHD. The ADHD brain lacks sufficient norepinephrine and dopamine, first affecting the amygdala, failing to calm it, causing outbursts or impulsive behavior. This explains common ADHD symptoms, which then affect the reward center. With low dopamine, the reward center stays understimulated and won't signal the prefrontal cortex to engage. That's why ADHD makes focus difficult or only possible under high stimulation. Exercise helps ADHD first by raising the amygdala's emotional threshold. A threshold is a boundary line. Higher boundaries make the amygdala less prone to rage. Second, exercise instantly boosts norepinephrine and dopamine, calming a reactive amygdala. In fact, ADHD medications work similarly by elevating these neurotransmitters. All right, let's recap part 1. Cognitive abilities rely on brain signaling through neural circuits formed by synaptic connections. Exercise boosts BDNF levels, promoting neuron growth and strengthening neural networks. Exercise also directly prompts the hippocampus to produce more neural stem cells, aiding memory. For attention issues like ADHD, exercise raises the amygdala's emotional threshold and boosts norepinephrine and dopamine secretion, stabilizing mood and boosting learning motivation. Now that we've covered cognition, let's move to the second question. How does exercise affect our emotions? In modern society, people often face stress from family, work, relationships, and other areas. Some feel mildly alert, while others feel completely overwhelmed, sinking into despair. So, how does stress impact the brain, potentially developing into emotional disorders like anxiety or depression?
When stressed, the amygdala, our brain's emotion detector, immediately sends signals.
Stimulating the adrenal glands, releasing different hormones at various stages. Initially, adrenals release norepinephrine. Once in bloodstream, it raises heart rate, blood pressure, and breathing. That's why stress makes you tense, heart pounding, and restless. Meanwhile, the hypothalamus receives signals, activating the pituitary gland. The pituitary gland is the body's master endocrine switch, pea-sized but regulating all hormone levels.
The pituitary directs adrenals to release cortisol, vital for human survival.
When your body senses environmental threats, it instantly prepares for rapid action. Fight or flight, let's examine how cortisol operates. Cortisol first acts like a traffic cop, signaling liver to convert fats and proteins into quick energy glucose. But this glucose only flows to stress areas like amygdala, hippocampus. Cortisol blocks other pathways, starving thinking regions and explaining mental fog under stress. With massive energy drained, cortisol directs food intake to restore blood sugar. This triggers intense cravings for high sugar and fat foods like donuts, bubble tea, ice cream. Their excess gets stored as abdominal fat. Since the abdomen is near the body's center of gravity, storing energy there doesn't affect balance during movement, so belly fat accumulates faster than limb fat. It's also where organs are located, so fat prioritizes abdominal storage for protection. That's why high stress often leads to weight gain. The amygdala also signals the hippocampus to map and record memories. When emotions are overexcited, increase GABA to inhibit impulses. When mood is too low, exercise boosts dopamine, norepinephrine, and BDNF, all enhancing glutamate activity. During emotional overexcitement, exercise broadly impacts the GABA system, which inhibits cellular hyperactivity, easing irritability, especially in women. Hence, the author emphasizes, exercise isn't about increasing or decreasing any single hormone, but achieving dynamic hormonal balance. Moving from hormones to aging. With current technology, aging is unavoidable. So how does aging occur? Microscopically, aging stems from three interconnected processes: cell death, capillary shrinkage, and synaptic atrophy. Let's trace this process starting from cell death. While using oxygen for function, brain cells also combat free radicals. What are free radicals? When oxygen contacts matter, oxidation occurs, like bananas turning brown. Inside humans, oxidation creates byproducts called free radicals. These hyperactive radicals lack an electron, so they steal electrons from neurons, proteins, fats, even DNA. Normally, the brain has a natural cleanup system to remove free radicals. But as we age, this natural cleanup system becomes less efficient. Uncleared radicals damage cells, compounded by DNA degradation in chromosomes during aging. Thus, genes responsible for protein production and cell repair stop working, and damaged cells can't be repaired, leading to death. As more cells die, the immune system activates, releasing white blood cells to clear dead cells. Normally, when white blood cells clear dead cells, inflammation occurs. For example, if you cut your finger, blood vessels dilate and redness appears. This is inflammation from white blood cells fighting bacteria or viruses. After healing, inflammation subsides. But with aging, constant brain cell death forms plaques, keeping white blood cells perpetually active, meaning the immune system continually attacks the brain, causing chronic inflammation. Healthy neurons then get attacked, Synapses deteriorate, connections sever, and signal transmission weakens. Reduced neural activity also shrinks brain-nourishing capillaries. This restricts blood flow, starving the brain of oxygen and nutrients, accelerating neuron death. Additionally, dopamine production decreases with age, and fewer new neurons form in the hippocampus. Hence, elders often show low mood and fading memory. Earlier sections explained how exercise increases blood volume, regulates energy, boosts neural activity and neurogenesis, all slowing brain aging. For elders, exercise crucially restores age-reduced dopamine, reigniting motivation and vitality. Starting exercise young is equally vital. By old age, you'll have a healthier, stronger brain with denser neural networks, better adapted and more resistant to damage. Now that we understand how the brain affects cognition, mood, hormones, and aging, how should we exercise scientifically? That's our fourth section's focus.
First, maintain intensity. At least 30 minutes of moderate aerobic exercise daily, 5 days weekly.
For seniors over 60, with more free time after retirement, exercising 6 days a week is ideal. If exercising 6 days a week, how should the workout load be distributed? The author suggests 4 days of moderate intensity exercise for about an hour, and the other 2 days of high intensity exercise for around 45 minutes. So, what is high intensity exercise? What is moderate intensity exercise? The author believes exercise intensity should be measured by heart rate. Higher heart rate means higher intensity, as some people are naturally good at running and find fast runs easy, while others struggle to finish even with full effort. Therefore, speed alone doesn't reflect exercise intensity. The widely accepted formula for maximum heart rate is 220 minus your age. If you're 30 years old, your maximum heart rate is 190.
High intensity is 70% to 90% of maximum heart rate, roughly 140 to 170 beats per minute. Moderate intensity is 65% to 75%, around 125 to 140 beats per minute.
Low intensity exercise is between 55% to 65%, about 105 to 125 beats per minute, ensuring both time and intensity.
The author advises a comprehensive mix of exercise types, ideally including 3 forms: aerobic, strength training, and complex movements for balance and flexibility. Aerobic exercise mainly refers to activities like brisk walking and running. The author recommends at least 4 days of aerobic exercise per week, 30 to 60 minutes at moderate intensity, to not only burn fat but also produce elements essential for altering brain structure. Strength training primarily refers to weightlifting or resistance machine exercises. The author suggests doing it twice a week, with 3 sets of machine exercises per session, each set repeated. 10 to 15 repetitions of strength training mainly aim to prevent osteoporosis, as muscles and bones age with time. Strength training effectively strengthens muscles and bones, while complex movements for balance and flexibility. These activities require technical skills. You need to maintain body flexibility and repeatedly practice movement techniques, thus engaging all brain neurons and activating a wide range of brain areas. Finally, the author hopes you'll stick with it. Statistics show about half quit new exercise plans within 6 months to a year. Why is it so hard to maintain? The main reason: people often start too intensely, making them physically and mentally miserable, so they quit.
If you're new to exercise, start gradually. Walk stairs instead of elevators. Stroll around buildings during lunch.
After adjusting to brisk walking, slowly add jogging, running, and complex movements.
For running, weightlifting, or yoga, always train under professional guidance.
Life lies in movement, and the reverse is equally true. Movement lies in life. The author mentions sea squirts, born with brains made of simple spinal cords and approximately 300 neurons. Within 12 hours of birth, they must find coral to settle on or die. Fascinatingly, after settling, they digest their own brains since movement stops, then live plant-like forever. For us humans, the crown of creation, we need movement and healthy brains. May this knowledge inspire you to make exercise part of daily life. That wraps up the book. Feeling inspired to lace up and run right now? Share your exercise plans in the comments. This concludes our exploration of Exercise Transforms the Brain. Show notes below. See you next time.